Today, we're tackling an invisible engineering marvel that's operating all around us. Think about it. How do we safely stop some of the most massive, fast-moving objects on the planet without ending up in a fiery disaster? Well, today we're diving straight into the brilliant engineering behind dynamic braking.
Okay, here's a quick look at our roadmap. First, we'll look at the problem with friction. 2, enter dynamic braking. 3, where does the power go? 4, the physics of stopping. 5, designing the circuits. And finally, 6, real-world applications.
Let's jump right into Section 1, the problem with friction.
So, picture this. How do you stop a massive, heavy freight train that's rolling down a steep mountain without just completely burning up the brakes? Traditional friction brakes rely entirely on physical contact, literally just pads rubbing against wheels. But on a continuous, steep downhill grade, all that friction generates an unbelievable amount of heat, and that triggers a highly dangerous phenomenon called brake fade. This is where the mechanical components overheat and, quite literally, lose their ability to stop the vehicle. There's just no way around it. We absolutely needed a better, safer way to stop.
Which brings us to Section 2, enter dynamic braking.
Now, the ingenious solution to this terrifying problem is dynamic braking. Instead of relying on mechanical friction, engineers decided to use electricity and magnetism. It's actually brilliant. When an operator needs to brake, they cut the main power to the electric motor. But because of momentum, the wheels keep spinning, which forces the motor's internal rotor to keep turning too. This mechanical rotation temporarily transforms the motor into a generator. And because creating that electrical energy requires actual mechanical work, it places a massive electromagnetic drag on the entire system, which smoothly slows the machine down. It's basically using the motor's own power against it.
All right, moving to Section 3. Where does power go?
So you might be wondering, once all that kinetic energy is converted into electrical energy, it can't just vanish, right? The energy has to go somewhere. Engineers manage this through two primary architectures. First up is rheostatic dynamic braking. Here, the generated electricity is routed into large onboard banks of heavy-duty resistors. You can think of these kind of like giant electric toasters. They take that energy, turn it entirely into waste heat, and powerful fans just blow it away. The alternative? Regenerative braking. Instead of just wasting the power as heat, this acts like an energy recycling system. It feeds the electricity back into the power grid or routes it straight back into the main battery pack of something like an electric car.
Let's look at Section 4, the physics of stopping.
Now, to master this transition from mechanical movement to electrical energy, we kind of have to bridge our terminology. Horsepower is our classic term for mechanical energy, but in the electrical world, energy is measured in joules or watt-seconds. The magic conversion factor that connects the two? 746 watt-seconds is equal to exactly 1 horsepower. That's our bridge.
So when we want to capture that energy electrically, we use capacitors as our, energy storage buckets. And to figure out exactly how big our bucket needs to be, we use a simple equation. W equals 1/2 C times E squared. W is the energy in watt-seconds, C is the capacitance value in farads, and E is the voltage. Basically, this just tells us the exact size of the capacitor required to catch the momentum of whatever load we're trying to stop.
Let's actually see how this plays out in an industrial setting. If engineers are designing a dynamic braking system, say for an Eaton adjustable frequency drive, they need some very specific mechanical properties. They start with the motor's horsepower rating. Then they calculate the total inertia, which is represented by the variable Wk squared. This accounts for the inertia of both the motor itself and the heavy load it's carrying. By combining those variables with the required change in speed, they can calculate the exact braking torque needed.
And once engineers calculate that required braking percentage based on the torque they're looking for a very specific threshold, 15%. This is absolutely crucial. If the braking requirement is under 15% of the drive's rated power, external dynamic braking isn't actually required. The natural power losses within the motor and drive are enough to dissipate the energy safely. But if you cross that 15% threshold, those internal losses just aren't going to cut it. You absolutely must install external dynamic braking hardware, like a brake chopper and a brake resistor, to safely absorb the load.
Let's get into Section 5, designing the circuits. Let's look at the actual engineering blueprints for these systems, using a DC motor on a model airplane propeller as our case study. Our first option here is the capacitor storage method. During normal operation, the motor is powered, and a massive capacitor is simultaneously being charged up. When power is cut, the motor just coasts. But when the brake is engaged, a switch connects that charged capacitor to the motor in reverse polarity. The stored energy delivers power in the opposite direction, creating a heavy dynamic braking effect to instantly stop the propeller.
But there's a catch, right? To time this perfectly so the propeller doesn't just stop and then violently spin backwards, we need to know exactly how fast that capacitor discharges. Enter the RC time constant. By simply multiplying the capacitance value by the resistance value, you get the exact time in seconds that it takes for a capacitor to discharge down to roughly 37% of its original voltage. It's a remarkably simple but powerful tool.
And using that RC time math, engineers can vastly improve the design. Instead of a massive, heavy capacitor storing all the braking energy, a smarter circuit uses the existing power source to provide the braking. This is controlled by a lightweight relay and a small capacitor. And to perfectly tune the timing, an adjustable 25-ohm potentiometer is added to the mix. By just turning the dial, you change the resistance, which changes the RC time constant. This allows you to dial in the exact fraction of a second needed to brake the propeller, without throwing the whole thing into reverse.
In action, this brilliant design plays out in 4 rapid steps. 1. Main power to the motor is cut. 2. The small, charged capacitor immediately powers the relay coil. 3. That relay actuates and temporarily reverses the motor's polarity to supply the braking force. And finally, step 4, within tenths of a second, governed by our RC time constant, the capacitor discharges, safely releasing the relay and disconnecting the power at the exact millisecond the propeller stops turning. Pretty cool, right? Which leads us to our final part, Section 6, Real-World Applications. In large-scale manufacturing, variable frequency drives handle this dynamic braking using a component called a brake chopper. See, when a heavy load slows down, it feeds energy back into the system, and that causes the DC bus voltage to aggressively spike. The drive's internal brake chopper actively monitors this. When the voltage hits a dangerous threshold, the chopper switches the dynamic brake on, routing that excess energy to a resistor to bleed off the voltage, and then immediately switches it off again. It literally chops the voltage down to keep the system safe.
And honestly, we rely on this technology everywhere. In rail transport, it's used for regulating downhill speeds for massive diesel-electric freight trains, completely eliminating the risk of brake fade. In industrial hoists and cranes, it is absolutely critical for preventing multi-ton vertical loads from just free-falling during a heavy descent. And of course, in electric vehicles, it's the foundational technology for regenerative braking, seamlessly blending with friction brakes to stop your car while simultaneously capturing energy to extend your battery range.
But as amazing as it all is, we do have to acknowledge the limitations. Because a generator requires rotational movement to actually produce electricity, dynamic braking force drops off sharply as a system slows towards 0 RPM. It physically cannot hold a vehicle completely still on a hill. For that reason alone, traditional friction brakes remain absolutely vital as a backup and for stationary holds. Plus, the equipment footprint for all those giant resistors, electronics, and cooling fans can be quite large and pretty costly up front. So, dynamic braking took the massive, dangerous problem of wasted heat and mechanical failure and turned it into an elegant electrical solution. But here is the real question. As industrial loads grow ever heavier and our global demand for energy efficiency absolutely skyrockets, how will we engineer smaller, smarter dynamic braking systems to capture every last drop of that wasted kinetic energy? It's the next great engineering frontier. Keep asking questions and